In this presentation, I am going to explain the previous GATE questions and answers for the year 2023, and the topic covered is electrical machines. Now let us see 2023 GATE question that carries 1 mark. The following columns present various modes of induction machine operation and range of slip. So the modes of operation is represented by in the column A, and the range of slip is represented in the column B. Therefore, in column A, the different modes of operation are, that is represented in small a, running in generator mode, and small b, running in motor mode, and small c, plugging in motor mode. Therefore, these are the three modes of operation, and the slip range are in column B, P from 0 to 1, Q from 1 to 2, and R from -1 to 0. Therefore, this represents the range of the slip, and this represents column A represents the modes of operation. The correct matching between the elements in column A and those of column B, what is the correct matching? Therefore, the options are column A is matched to R, B is matched to P, and C is Q. That is the option A. And option B, AR, BQ, and CP. Option C, AP, BR, and CQ. And option D, AQ, BP, and CR. So these are the matching of this modes of operation to the corresponding slip range. Now coming to the torque slip characteristics of an induction machine as such. Here, this is the representing the torque slip characteristic. And when the machine is operating in as a motor, that is this region where slip is marked in this direction. When slip equal to 0, it is called the synchronous speed. That corresponds to synchronous speed. And when slip equal to unity 1, that represents the stationary. That is when the rotor is stationary. That's represents. Therefore, this is representing the motor mode of operation of an induction machine. That is A, running, that is B, running in a motor mode. B, that is represented by the slip is changing from 0 to 1. That is B and P. That is B and P that's representing here. And the second here, if you see that S is less than 0, that is when slip equal to -1 to 0 here, when a negative slip happens, N is more than Ns, because slip equal to Ns minus N divided by Ns. Ns minus N divided by Ns. And when rotor speed is more than the synchronous speed, when N is more than Ns, we will be getting a negative slip, or this mode of operation is called the generating mode of operation. Generating mode of operation means the beacon generator, that is A, that is happening when from -1 to 0. That is equal to R. AR. Therefore, AR and BP, and finally it will be CQ also comes. Therefore, the option A is the correct answer, in which this is the motor mode of operation, and this is the generator mode of operation, and the last one is the plugging, or that is when the range from S equal to 1 to 2, that is operating in a plugging mode of, that is C. Therefore, the correct answer is that option A. Now let us see the another problem, 2023 GATE question that also carries 1 mark. A 10-pole 50 Hz 240 volt single phase induction motor runs at 540 RPM while driving the rated load. The frequency of induced rotor current due to the backward field is, options are A, 100 Hz, B, 95 Hz, C, 10 Hz, and D, 5 Hz. Now coming to the torque slip characteristics of a single phase induction motor, this is representing the torque slip characteristics of an induction motor that indicates that starting torque, when S equal to 1, that is starting torque equal to 0. Therefore, in a single phase induction motor, starting torque equal to 0. For this, that can be split into two. One, the torque due to the forward field. Another is the torque due to the reverse field. Therefore, this is representing the torque slip characteristic due to the forward field, and this is representing the torque slip characteristic due to the backward field. The summation of this one represents the total torque slip characteristics, which you can see that one at the initially the torque slip, the initial torque when S equal to unity or stationary, starting torque, that is equal to 0. Now coming to the problem here, supply voltage equal to 240 and the frequency equal to 50 Hertz and the rated speed of the motor it is equal to 540 RPM. First we have to calculate what is the synchronous speed corresponding to 50 Hertz and the number of poles equal to 10. Therefore 120 F by P is the synchronous speed Ns, which is equal to 120 into 50 divided by 10. 600 RPM is the synchronous speed of the motor. Now coming to there are two fields I'm telling you. That is one we call that is rotating in the forward direction, the same as the motor, and another field is rotating opposite to the rotor. That is a backward field. For the forward field, that slip corresponding to that one equal to Ns minus N divided by Ns, or it equal to 600 minus 540 divided by 600 or 0.1 or 10% is the slip corresponding to the forward field. And the backward field is rotating opposite to that one, and the corresponding slip is equal to Ns minus N. Since it is a reverse one, the rotation of the rotor with respect to field is reverse, so that is why it is called minus N. For Ns plus N divided by Ns, or 600 plus 500 divided by 600, or equal to 1.9. Therefore the backward slip SB equal to 1.9, and the frequency of the induced rotor current due to the backward field can be calculated, which is equal to the backward slip into the supply frequency, which is equal to SB into F, or which is equal to 1.9 into 50 equal to 95 Hertz. Therefore the answer is option B. Let us see another problem, 2023 gate question that also carries 1 mark. The four stator conductors A dash and B dash of the rotating machines are carrying the DC currents of the same value, the direction of which are shown in the figure 1. Here these directions are going. Therefore the current is entering into that one. This is the current is leaving here. Therefore A dash. Similarly B dash. That's also shown, which are shown in the figure 1. The coils A dash, small a dash and B dash are formed by connecting the back ends of the conductors A dash and B dash. Therefore, small a dash and B dash are representing the rotor winding. Here A dash and small B dash, and that is connected in this fashion, A dash and B dash. The EMF induced in these coils A dash and B dash are represented as by A dash and B dash. That is the induced voltage in coils A dash and B dash. If the rotor is rotated at a uniform angular speed of omega radians per second, this is the rotor that is rotated at omega radians per second in clockwise direction, then which of the following correctly describes A dash and B dash? The option A, A dash and B dash have finite magnitude and they are in same phase. Option B, A dash and B dash have finite magnitude and B dash is leading A dash. Option C, A dash and B dash have finite magnitude and A dash is leading the voltage B dash. The option D, both A dash and B dash both are equal to 0. So these are the four options. Now let us see the answer in the next coming slide. Now continuation of the same problem. The coils A dash and B dash, that represent the rotor coils. A dash and A dash and coil B dash, that represent they are positioned along the neutral axis or Q axis. Now let us see what is that one. Here the stator conductor, that is the current through this one, that is entering into this point. Therefore that is the magnetic field produced by that current is that direction is in this fashion, because that is obeyed by the right hand thumb rule. that the current direction through this one is in this. Similarly, in this case, the current is going out, or here the corresponding magnetic field is in this direction. Therefore, this is the clockwise direction and this is the anti-clockwise direction. Therefore, these are the directions of the current through the stator. And if you see that one, here the neutral axis is the axis which is perpendicular to the magnetic field. Therefore, which is perpendicular to magnetic, this is the magnetic field. And here you can say that these are the magnetic field they are adding. Or perpendicular to the magnetic field axis is this one. This is the q axis. And there here also perpendicular to this one, this is the perpendicular to the. These are the q axes. Q axis. And the axis perpendicular to that one is called the direct axis, or that will be the same as in the magnetic field. Therefore, here see that one, the magnetic field is in this direction. So here also the magnetic field is in this direction, and here also the magnetic field is in this direction. Therefore, this is representing the, of course, the north pole. And here also, if you see that one, this is representing in this direction, and here also representing this one. Therefore, this is representing the south pole of the stator. Therefore, north pole of the stator and south pole of the stator. Therefore, this axis perpendicular to that axis is called the q axis, and this is called the direct axis, d axis. Now, that is the d axis, q axis, which is perpendicular to the magnetic field axis produced by the stator conductors. And this orientation means the magnetic flux linkage through this coil is at its minimum. Therefore, in that case, the magnetic linkage is minimum, and the flux linkage through the coils is at its minimum, and therefore the EMF induced in the other coils A and A dash and B dash is equal to 0. Since the q axis, here can say that A dash is in along with the q axis of this one. Similarly, B dash is along the q axis here. Since it is along the q axis, the voltage induced in this coil A dash and B dash is equal to 0. Therefore, at this instant, the coil A dash and B dash have along the q axis. So, there is no induced EMF in both the coils A dash as well as B dash of the rotor. Or the rotor induced EMF A dash, which is equal to B dash, which is equal to 0. Therefore, the answer is option D. The answer is this option D. Now let us see another problem, 2023 gate question that carry 2 marks. A separately excited DC motor which is rated at 400 volts and 15 amperes, 1500 RPM drives a constant torque load at rated speed operating from a 400 volt DC supply drawing the rated current. Therefore, this is DC supply drawing the rated current. That one. This is a separately excited DC motor. The armature resistance equal to 1.2 ohm. And if the supply voltage is reduced by 10%, if this voltage is reduced by 10%, with the field current unaltered, this field current is not changed, then the resultant speed of the motor, what is the speed of the motor? When the rated voltage, the speed was 1500. When the voltage is reduced to by 10%, what is the speed of the motor, keeping the field current same? Now, that is to be, what is the resultant speed of the in RPM, that is round off to the nearest integer. That is separately excited DC motor. This is a separately excited DC motor in which the flux is a constant, the field current is a constant, the flux is equal to constant, phi is equal to constant, and the rated speed is equal to 1500 RPM, and the rated voltage is equal to 400 volts, and the armature resistance is given as 1.2 ohms. Now, corresponding to the rated speed, now let us see what is the back EMF. For the rated current equal to 15 amperes, at the rated speed, back EMF can be calculated as the supply voltage V minus the drop due to the armature resistance. Therefore, V minus IARA, which is equal to 400 minus 15 into armature resistance 1.2 ohm, which is equal to 384 volts. Therefore, the back EMF corresponding to the rated speed 1500 RPM equal to 384 volts. Now, continuing the same problem, separately excited DC motor. When the input voltage is reduced by 10%, means that previously it was 400 volts, now it is reduced to 10% or 0.9 into 400, which is equal to 360 volt is the voltage that is applied across the armature. And we have seen that load torque is a constant. Since torque can be torque equal proportional to phi into Ia, or it is equal to a constant phi into Ia. Therefore, the torque is constant. Therefore, torque is Ia is also rated current is also not changing. Therefore, Ia equal to 15 ampere, that is also not changing. Therefore, here since the flux torques are not changing, that is flux is not changing. Similarly, the armature, since the constant torque is happening, because we are considering the constant torque, Ia is also constant because T is proportional to phi into, or T equal to constant K into phi A. Flux is a constant. Torque is also constant in the problem which is given. Therefore, the armature current also constant. Ia is also constant. Therefore, in the second case, when the voltage is reduced by 10%, the corresponding armature current is same as the previous, or Ia equal to 15 amperes. Now again coming to the back EMF corresponding to the second case, then voltage is reduced by 10%, that is E1, which is equal to V1 minus Ia1 divided by, into Ra, or it is equal to, the voltage is now 360 minus same current here because torque is constant, 15 into 1.2, or that's equal to 344 ohms. Therefore, the back EMF corresponding to the second case, or when voltage is reduced by 10%, equal to 344 volts. Now, as we know that the speed of the motor and the back EMF as well as flux is related by N is proportional to EB by phi, or E by phi. It's represented by E by phi. Or first case corresponding second case, when voltage is reduced here, N1 is proportional to E1 divided by phi 1, because but phi equal to phi 1 because the flux is not changing. Therefore, you can say that this reduced equation can be written as N1 by N. N1 is the speed of the motor when voltage is reduced by 10%. Then N equal to E1 by E. Or we can say that N1 equal to E1 by E into N, or E1 equal to 344, or 344 divided by corresponding to the rated speed, we have already calculated 384, into corresponding the speed, rated speed 1500, or we can get 1343 rpm. Therefore, when the voltage is reduced by 10% for the same torque, load torque, and keeping the flux constant, the corresponding speed is reduced to 1343 rpm. Therefore, the answer is 1343 rpm. Now let us see another problem. 2023 gate question that carries 1 mark. That is a three-phase synchronous motor with synchronous impedance ZS 0.1 plus J 0.3 per unit per phase has a static stability limit of 2.5 per unit. The corresponding excitation voltage in per unit is this, so round off 2 decimal places. Therefore, this is the question. Now here the synchronous impedance is given as 0.1 plus J 0.3, or it equal to 0.316 angle 71.56 in polar coordinates. But the stability limit is given as 2.5 per unit, and excitation voltage is the question, that is represented as E. The maximum power output of a synchronous motor, the equation EV divided by ZS minus E square by ZS into the resistance RG. Therefore, here RG means 0.1. For this is the equation in which the maximum, that is the stability limit Pmax is given as 2.5. Therefore, the 2.5 equal to E is unknown into, but we are considering the voltage V, which is equal to 1 per unit. Therefore, 1 divided by ZS is given as 0.316, or that is the magnitude 0.316, minus E square divided by 0.316 square into this 0.1, that is RG. So from this equation, we can calculate the excitation voltage equal to in per unit 1.58 per unit. Therefore, in the synchronous motor, the excitation required, or that excitation value is equal to 1.58 per unit. Now let us see another problem, 2023 gate question, and that carry 2 marks. A 3-phase 415 volt 50 Hz 6 pole 960 rpm 4 HP squirrel cage induction motor drives a constant torque load at rated speed, operating from a rated supply and delivering rated output. If the supply voltage and frequency are reduced by 20%, the resultant speed of the motor in rpm, neglecting the stator leakage impedance and the rotational losses, that is the speed of the motor in rpm, that is round off to the nearest integer. Now coming to the induction motor, the synchronous speed of the synchronous motor is that is and that is corresponding to the supply voltage of 50 hertz, that is represented as ns1, corresponding to 50 hertz ns1, or that is the corresponding to frequency, sorry, ns, this is corresponding to a frequency of f1, the corresponding ns1 equal to 120 f1 by p, or we can say it is equal to 120 into 50 divided by number of poles 6, or 1000 rpm is the synchronous speed corresponding to the supply frequency of 50 hertz. And now let us see the corresponding slip. Rotor speed is given by 960 rpm. Therefore, the slip is given by ns minus n divided by ns. Therefore, 1000 minus 960 divided by 1000, or 0.04, or that's also equal 4%. Therefore, at the rated speed 960 rpm, the slip of the motor is equal to 0.04. Now, the air gap torque of an induction motor, there's an approximate equation like this one. The air gap torque is proportional to the supply voltage square divided by slip, into slip divided by frequency. Therefore, T is proportional to V square S divided by F. This is an equation relation is the T is proportional to V square S divided by F. Now here it is given that torque is a constant load torque is that. Meaning that if you put it as here, since the load torque is a constant, motor torque, load torque is constant, the motor torque is also constant, meaning that T1 equal to T2. That is, second case torque is same as the first case torque. That is, when the frequency and voltage are reduced, that's I am considering a second case. Then that torque is same as the torque 1, or T1 equal to T2. That torque is proportional to V square S by F. Therefore, you can say that one corresponding to the first case, voltage I am representing as V1. V1 square S1 divided by F1. Second case corresponding to V1 square divided by S2 divided by F2. Both are equal. So, we got T1 equal to T2. Therefore, the voltage and frequency are reduced by 20%. Therefore, the voltage V2 is equal to 0.8 times V1, and the frequency F2 equal to 0.8 times F1. Now let us see the continuation, the next slide. Now continuing the same problem, as we have seen, since the load torque is constant, we can say that T1 equal to T2, or V1 square S1 divided by F1 equal to V2 square S2 by F2, where V2 equal to 0.8 times V1 and F2 equal to 0.8 times F1. That is given in the problem, because 20% reduction is the voltage and frequency are reduced by 20%. Therefore, V2 equal to 0.8 times V1 and F2 equal to 0.8 times F1. Substituting in this one equation, V1 square S1 divided by F1 equal to 0.8 V1 all square into S2 divided by 0.8 F1. Or from this equation, we can get it as S2 equal to S2 divided by 0.8 equal to 0.04 divided by 0.8, which is equal to 0.05. Or we can say that or the slip corresponding to the second case equal to S1 by 0.8, or which is equal to 0.05, or 5% is the slip corresponding to the second case where the voltage and frequency are reduced by 20%. Now the new synchronous speed, when the voltage and frequency are reduced, synchronous speed will be changing, which is equal to 120 F2 divided by P. 120 into frequency is now 0.8 times 50 divided by 6, or equal to 800 rpm is the new synchronous speed. That is, when frequency is reduced by 20%, the new synchronous speed is equal to 800 rpm. Therefore, the slip is also given as 0.05. Then the rotor speed corresponding to the second case, that is equal to 1 minus S2 into the corresponding synchronous speed. Therefore, it is equal to 1 minus 0.05 into 800, or it is equal to 760 rpm. Therefore, then the voltage and frequencies are reduced by 20% so as to keep V by F constant. That is, then the motor speed is reduced to 760 rpm. Therefore, the answer is 760 rpm. Now, let us see another problem of 2023 gate question, and that carry 2 marks. When the winding CD of a single phase that is single phase 50 Hertz, 2-winding transformers are supplied from an AC current source of frequency 50 Hertz and the rated voltage of 200 volt RMS or 50 Hertz is obtained at the open circuit terminals of the AB. The cross-sectional area of the core is 5000 millimeter square and the average core length traversed by the mutual flux is 500 millimeter. The maximum allowable flux density of the core is Bmax equal to 1 Weber per meter square and the relative permeability of the core material mu r equal to 5000. The leakage impedance of the winding AB and the winding CD at 50 Hz are respectively 5 plus J 100 pi into 0.16 ohms and 11.25 J 100 pi into 0.36 ohms respectively. Considering the magnetizing characteristics to be linear and neglecting the core loss, the self-inductance of the winding AB in millihenry is round off to 1 decimal place. Therefore, this is the transformer in which here 50 Hertz AC current is supplied and the secondary induced voltage, that is 200 volt 50 Hertz. Now we'll be continuing the next slide. Now continuing the same problem. The cross-sectional area is given as 5000 millimeter square and the length of is given as, that is flux path, that is 50 millimeter. Maximum flux density equal to 1 Weber per meter square and the relative permeability equal to 5000. Induced voltage, basically the induced voltage transformer, the induced voltage equation is equal to 4.44 5 mf N1. That is the basic equation of the transformer induced voltage. Therefore, the induced voltage equal to E1 equal to 4.44 5 mf into N1, where E1 is given as 200 and phi m can be calculated as Bm into area. Therefore, it is equal to Bm is 1 Weber into area. Area equal to 5000 millimeter into 10 raised to minus 6 and into the frequency equal to 50 and the number of turns is the unknown one and that can be calculated as 180 is the number of turns of this. Next, leakage impedance of the winding AP and CD are Z1, ZL1 and ZL2. That is given in the problem. It is 5 plus J 100 pi into 0.16. This is actually 2 pi F that is into L. Therefore, this is the leakage impedance of the one side and this is the leakage impedance of the another side. Therefore, the secondary as well as primary as such. Therefore, we can calculate what is the leakage inductance, magnetizing inductance. That is, magnetizing inductance can be calculated as N square by reluctance because N is already calculated as 180. N square divided by reluctance is the magnetizing inductance, which is equal to N square divided by L divided by A mu 0 mu r. Substituting in this equation, we will be getting it is equal to 2039 millihenry or 2.039 Henry is the, it is equal to the magnetizing inductance. Now the self-inductance of the winding, that's the question. In order to find out the self-inductance of the winding, the total self-inductance of the winding is the sum of the leakage inductance and the magnetizing it. The leakage inductance in this one winding, this is equal to the leakage inductance of this winding is given as 0.16. Therefore, the 0.16 plus 2.039 or that is equal to 0.16 plus 2.039 which is equal to, that is the total self-inductance of the winding is the sum of the leakage inductance, that is 0.16, and the magnetizing inductance, that is this one 2.039. If you add that one, we'll be getting it is equal to 2.2 Henry or 2200 millihenry. Therefore, the answer is 2200 millihenry.